Hello, everybody. We have discovered that the speed of sound is about 340 meters per second in air. Speed of sound in air is 340 meters per second. And by the way, sound can travel through liquids. That's how whales and dolphins communicate, and through solids. So that's why you can hear sound coming along train tracks. But in liquids, it travels much faster than 340 meters per second, maybe 1,000 meters per second. And in solids, more like 5,000 meters a second, but it varies from material to material. It still travels as a longitudinal vibration. Now, what we're going to look at today is how to measure the speed of sound more effectively than we've managed so far. You see, at 340 meters per second, this is a lot slower than the speed of light, which is 300,000 kilometers a second. But nonetheless, even if you've got a distance of 340 meters, you're only timing a second, which is not a very long time to time with a stopwatch. So we've got a choice. We can either improve the timing device or we can increase the distance. I tried to improve the timing device by using a slow-mo camera. It wasn't entirely successful, and our data was not entirely compelling. There was a lot of inaccuracy. The data was spread all over the graph. So here I'm going to tell you about the way that we usually use to try and increase the distance. If we can increase the distance, then we can increase the time, and then we can measure it with a stopwatch. So we use the same idea of somebody standing with two bits of wood, which I'll show like that, which they're going to go clack, clack, clack. They're going to make a bang. But this time, we also have some wall or other, some nice, convenient high wall, and the sound can reflect off the wall. I better get this person on the ground. You might be able to do this in your garden and bounce the sound off the front or back of the house. I don't know. Usually I do it out on Newfield, and we bounce the sound off the wonderful facade of Science School. Anyway, this distance, which I'll call D, may still only be 100 meters. So therefore, the sound is going to get 100 meters. Well, it goes there and back. So that's 200 meters. So here comes the clever bit. When we hear the sound, we make another clack in time with the echo. So in effect, we make a clack, and then the sound of the clack goes to the wall, and then it rebounds, comes back, and gradually we adjust the timing of the clacks until the new clack is in time with the old clack. The new clack is in time with the echo clack. And we might therefore say, well, okay, what we're going to do is we're going to time how long it takes to go backwards and forwards and backwards and forwards and backwards and forwards, maybe 20 or 30 times. Okay, so if we time, say, n transits, then we get a speed. Speed is distance over time. Okay. Well, the total distance for each transit, it's 2d, and for n transits, it's n times 2d, and t is the total time. So that's measuring the speed of sound using the echo technique. It's not particularly interesting scientifically, but they do like us to tell you about it. Now, the other thing we usually do, we may do this when we finally get back together again, is we use another much more effective timing device. So that's the echoes technique. So I'm just going to finish by telling you about the two microphones technique. This is really clever, and I'm sorry we're not able to do it together. What we do is we put a microphone over here. This is the symbol for a microphone. And then we have another microphone over here. And then we feed the signal from each of these into a device that's called a cathode ray oscilloscope. Now, this is a bit like the heart monitor that you see in hospitals, where it goes bip every time the heart goes bip. And then we add in our clacking machine again, so we make a sharp sound. And what happens is, on the cathode ray oscilloscope, it's basically a voltmeter, so the voltage generated by the microphone causes the trace to go across, and we see the first trace like this, and this is microphone number 1. And then, if this is microphone number 2, the sound takes longer to arrive at microphone number 2. So then, with microphone number 2, I'll just draw it in a slightly different place. This is microphone number 2. So I've got number 2 in blue, and number 1 in black. And we can use the picture to find the time between the two pulses. And of course, we can measure the distance between the two microphones. Well, the CRO, will measure to the nearest millisecond or even microsecond. So that gets over the problem of the timer being too inaccurate when operated by hand. You can see by the two pulses how long the sound took to get from microphone number 1 to microphone number 2. So we end up with speed equals distance over time as usual. So we get distance between the two microphones is d, that's quite simple. And then t comes off the crow because we can see the two pulses. Now, to really get a nice, accurate, compelling result, we vary d, measure t. So we measure t for a variety of different distances d, and we'd expect then, if we plot a graph, that if we plot a graph of distance against time, then if you double the distance, you double the time, we'd expect it to be a straight line. And in this way, we get a good averaging technique, and the speed is the gradient of the graph. And there you have it for the speed of sound.